Other questions?
Do
Yes.
you want three speakers for the online epic, or just the write for one speaker?
I would just write up, make sure you hit the 500 words. You know, if you love one speaker and there's 500 words there, go ahead and do it. I don't care so much there. Okay, because it's going to be a panel, so it's going to be probably question and answer, whatever works best. Okay, other questions? Alrighty then, so let's go ahead, and what we're going to do today is we're going to finally develop and use the most important equation for this class. This is our big, beautiful equation here we're going to use. Use my pen though. Hold on. Sorry, a little disorganized up here, I guess. All right, so this is our big equation for the course, maybe the most important one. And so where we're headed to is this. This is the Gibbs free energy equation. And we're going to use it. The big thing we use this for is we use this for spontaneity. We use this for calculating how much energy a process produces, where that energy is a product of heat given off and entropy produced. Okay, when we think about that, super, super useful. But where we're going to start is we're going to start where we've been before. So we have the entropy of the universe can be the sum of the change in entropy of the system plus the change in entropy of the surroundings. Okay, where we're thinking about the surroundings here really are kind of some local measurement we're making, right? Part of the problem with this is some of the equations in terms of the surroundings is what's the temperature of the universe, right? We have equations where we're using temperature. We know the temperature of a water bath around our reaction. We don't know the temperature of the universe on average. Well, we probably do, but it's really small. So what we've got here then is we can take that equation, and if you remember, you know, the change in entropy for the universe for any process that happens has to be greater than zero, right? Entropy that's our second law of thermodynamics, that the entropy for any change, the entropy of the universe is always increasing. And then you remember, hopefully, that if I have my heat of my surroundings, how is my heat of the system related to that? It's negative, right? Any heat given off by the surroundings to the system is absorbed by the system, right? So we have a different, if heat, let's take it the other way. If the system gives off heat, the surroundings absorbs it, right? So we have a different sign there. And then we can talk about the change in entropy for the surroundings, right? That's a second part of this equation, this is what we're working on right here. And we can say that change in the surroundings is equal to the heat absorbed or given off by the surroundings and over the temperature. That would be the temperature of the surroundings here. But what we're working towards is this equation right here. This is just, we can use this just from the perspective of the system. Okay? So can use for just the system. Because we don't want to have to worry about what the whole universe is doing here. All right. What we want to worry about is a system that's easy to measure. We might be measuring things about the system based on what we see in the local surroundings. And so that we can restate this as we know that if the heat of the surroundings is equal to the negative heat of the system, right? Over temperature. And then I want to remind you, we've got this delta H thing. Delta H is heat. We have very recently, the last lecture, we were using this as heat of vaporization or heat of fusion, right? And that was per mole. But if I don't put vape or fusion there, this is just heat. It's the same as the Q, okay? So the heat, so we get that. All right, so this, what we can do is this, and so we can sub that in. So the change in entropy for the universe is going to be equal to change in entropy for the system plus, well, let me make it just minus delta H, so enthalpy, heat, enthalpy is heat, over temperature. And now if I want to turn this into the Gibbs free energy equation, I'm going to multiply both sides by -1 t or negative t. So if I multiply this by negative t, this is a minus sign here, right? So I have to multiply this by negative t, and I'm going to multiply this by negative t. And that's going to give me negative t delta S for the universe is equal to negative t times delta S for the system, right? And then over here I've got negative delta t times negative delta h, so it's going to be plus delta h, and that t cancels with that t. You guys with me for that? Okay. And all this is really going to be for the system, but we're going to drop the system subscript because we're lazy and because it's always for the system. You might not be lazy, but I am. So what I'm going to do is rearrange this here, but before I do that is I'm not going to rearrange it much. This we're going to call, this is the Gibbs free energy. So we're going to give it a name, okay? And we're going to give it a new symbol. Delta G is what we call it, okay? So we just abbreviate it like that. And then I'm going to change the order of things over here because it always gets written like this. That's our Gibbs free energy equation. This is our big, beautiful equation. This is the most important equation in the class. And it tells us lots of important stuff. All right. That's for the system. And the most important thing, or the most basic important thing it tells us is if delta G is negative, the process is spontaneous. So if delta G is less than 0, then the process is spontaneous. And I had some good questions last time. Okay, what do I mean if I say it's spontaneous? I mean if my reaction is A plus B goes to C plus D, we say it's spontaneous if it goes in that direction. Right? And if it's non-spontaneous, it would actually go in this direction. And if delta G was 0, it would go in neither direction. Okay? So we'll say, let me go ahead and put delta G less than 0 again with my green arrow, and delta G greater than 0 for my gray arrow there. Does that make sense? So that's what we mean when we say something spontaneous or not spontaneous. Let's talk about what this means in terms of these free energy diagrams we looked at before. I don't know, I may have called them free energy diagrams by accident, or I may have just called them energy diagrams or reaction coordinate diagrams. Lots of names for these sorts of things. But this is now I can call them a free energy diagram because I've defined free energy. And when we look at these diagrams, they tell us a lot of stuff. So this right here, this difference in energy between our reactants and our products tells us whether this is spontaneous or not. So for this reaction, if I think about going reactants to products, the products have a lower energy than the reactants, so my delta G is going to be less than 0. It is negative because these reactants give off energy. They lose energy when they become products. So think about the reactants becoming products as our system here. Does that make sense? If we do the reverse reaction, products to reactants, then delta G is going to be greater than 0. Okay? And in fact, all we would do, this is a completely reversible process the way written. So if we did the reverse reaction, we just flip the sign on whatever delta G is. Okay? Because instead of losing that much energy, they would gain that much energy. Okay, have to get the energy from the surroundings somehow. Questions on where delta G fits in this diagram? All right, and then the other part of the diagram we talked about when we were in kinetics, this is the barrier to getting from here to here. This is our activation energy. This determines how fast. This determines how much products we get. This determines how fast we get those products. Okay? It's kinetics, and this top is kinetics, the bottom is thermodynamics, and they're different. If instead our reaction went like this, if we let it go long enough, we would get just as much products versus reactants at equilibrium, but it would take a lot longer because the height of that barrier is higher. Does that make sense? So when I made this higher, the actual relative energies of my reactants and products did not change, but the barrier I had to get over did. Okay. Let's go on then and talk about how these pieces of this equation affect it. I want you to have a good feeling for this. I want you to be able to work without numbers. So this is our equation. Delta G is equal to delta H minus T delta S. All right. If I had a piece of ice and I put it on this table, what would happen? It would melt. Is it absorbing heat or is it giving off heat when it melts? What was that?
Absorbing.
It's absorbing heat to melt, right? Those molecules have no energy, they have little energy, and then they have to get more energy, right? You have to break bonds. So it's absorbing heat. So that means delta H, that's our heat. Is that positive or negative? Is heat going into it or coming out? It's positive. So ice melts. Okay, so this is positive. So that's going to make this process positive, right? For this to be spontaneous, and it is spontaneously melting, right? This has to be negative. What about the entropy? Does it become more disordered as it melts or more ordered? More disordered, so entropy increases. So this is positive, right? What's the temperature in Kelvin? Is it positive or negative? It's always positive, right? You're never going to have anything happen at zero. So this is always positive, and then it's times a negative, right? So overall, this term is going to be negative, and it's going to contribute negative stuff to this. All right, so this is where we think about the temperature effect. So we've got things that are opposing each other, right? We have a positive contribution and we have a negative contribution. And how do we sort that out? Well, the temperature is going to determine whether this happens or not. And this fits for the daily experience, right? So at low temperatures, really low temperatures, does my ice melt? No, it doesn't melt. We know that. Our freezer ice doesn't melt. And the temperature is low, so this term is small, right? At high temperatures, as you raise the temperature, eventually you get to a point my ice melts. This temperature keeps going up until this term is more negative than this one is positive, and then it's spontaneous. Does that make sense? Okay. Let's see, what did I do for my other one? So what I wanted to do is I want you to answer, this is like a multiple choice question. I like these sort of questions. You very well may get this. Is the formation of rain spontaneous? From clouds, spontaneous. All right, clouds are gaseous water, right? And rain is liquid water. And what I want you to answer is it spontaneous always? At high temperatures? At low temperatures? Never. All right, and don't worry about snow. And the way I want you to reason it is, you form liquid water from gas, what's this term? Is it positive or negative? What's this term? Is it positive or negative? Give you a minute or so to look at that, and then we'll go over it. Yes.
Can I ask you a question about the
Absolutely.
actual like entropy? I feel like I'm a little confused about.
Sure.
I know that entropy could be extreme.
Is it positive? Is the liquid more disordered or less disordered? Okay. Does that help? That's just a question of input.
How do we find the? You said entropy is heat.
Yes. So is heat going to be given off when you go from a gas to a liquid? So one way to think about that is whenever you make bonds, you give off energy. Whenever you break bonds, it takes give you 30 more seconds.
Like, the bond to me.
Okay, let's go ahead and look at this. So we've got rain forming from clouds. Let's do this one part right here. All right. Water is condensing. Do I give off heat or do I absorb heat? Let's do, if you're not sure, let's do the opposite process, right? Because the opposite will be, if water condenses, what if I make water into a gas, does it absorb heat or give off heat? It's pretty obvious it absorbs when it becomes a gas, so it's got to give off when it becomes a liquid, right? So if you have one of these processes, they're reversible, the reverse thing happens, think about the easier one if you have to. Switch over to the easier one. So this, we're going to give off heat, which means delta H is negative or positive? Negative, right? We're losing energy when you make rain, okay? The water loses energy. How about the entropy? So when I go from a gas to a liquid, do I lose, is entropy negative, meaning that it's more ordered, or is entropy positive, meaning it's more disordered? Negative, okay? So we've got a negative here, but remember this has a negative out front, right? So overall, this thing is positive. Does that make sense? Right? In terms of the term, I've dropped the temperature. We'll go ahead and put the temperature in, right? Because we're going to need it in a second. So we've got, so this is overall positive, this is negative, they're opposing each other, right? We're thinking about how do these affect this? They make it more negative or more positive. So as the temperature goes up, right? They're opposing, so it's got to be one of these two, right? It can't always be something if they're opposing. As the temperature goes up, does this process become more spontaneous or less spontaneous? This term is positive and it becomes bigger as the temperature goes up. Less spontaneous, right? So rain will form at low temperatures. And at high temperatures, as this goes up and up and up, eventually this positive term outweighs that term. Does that make sense now from experience? If I raise the temperature on Earth to 120 degrees Celsius, we're all dead. But is it going to rain? Is water going to condense?
Probably not.
No. Yes.
So in this scenario, when the rain is forming and it's losing energy, is that energy then being given to like the clouds? Where is that energy going?
So it is. So it would heat up the air. Actually,
Okay.
You're giving off, but it's giving off heat. Let's not say energy.
Oh, okay.
Let's actually say heat because the enthalpy, the delta H, is heat. And heat is a form of energy.
Yeah.
But more specifically, delta H is always heat.
Okay.
Other questions? All right, good questions. Priscilla? No.
Yeah, I'm just, so you said if T is, if delta S is low, then T is supposed to be high.
I'm sorry, what was that?
I'm trying to figure out how they're opposing, you said delta.
How they're opposing
Yeah.
in terms of signs? Let me write the whole equation here and then put it next to it. That might help. So we've got delta H minus T delta S, okay? And so if we put all the signs in here, I'm going to put all the signs on top and then I'll put the sums in the bottom, right? So heat is, there's only heat, right? So on the bottom, that's going to be only negative. So it's making delta G negative, okay? But it's fixed. It doesn't change. And then over here, we said we were going to, from a gas to a liquid, so that's a negative, we lose entropy, it's more ordered. This is, temperature is always positive. And so we have a negative times a negative. That's going to make this positive overall. But this term changes with temperature. As temperature goes up, we get more and more positive. Does that help? Okay. And so, and then based on just experience, you know if it's, well, you don't know from your experience, right? But we know if we raise the temperature versus 120 degrees, it's not going to rain because water isn't going to condense. Okay. Other questions? All right. So you should be able to answer questions like that. You get a process, you should be able to reason through, is heat given off? Is entropy increasing or decreasing, and then decide whether it'll be spontaneous under one of those four conditions. Let's see. So then also you should be able to just use this equation straight out to calculate things. All right, remember, this is our most important equation. I want you to just go ahead and do A. I'm going to give you the equation again. I'm not even going to run an example for this. Yes, absolutely. Thank you. Okay, so do A. And they were very nice to you for A. If you did B, what would you have to do? You'd have to convert temperature and you'd have to make sure these units matched, right? You'd have to put both in joules or both in kilojoules. Call me over if you have questions. We'll try to reorganize this. Okay, let's go ahead and look at this. So we've got, this is just kind of plug and chug. We're going to put the numbers in, okay? So we can use this to decide whether this reaction is spontaneous or not. I've got 530.05 joules for whatever this process is for the heat, right? And then the change in entropy, we're at 298 degrees Kelvin. That's times, our change in entropy is negative 8.1 joules Kelvin. All right, and so I can go ahead and add these together. 5305 plus 298 times 8.1 and I get, I've got two significant figures over here, so, oh, but it's an adding bit. All right, so actually correct significant figures is going to be, sorry, it's going to be this. I'm sorry, that's not actually the answer. It's going to be this, I think. Okay, so that would be our answer there. So is this process spontaneous or not spontaneous? It's not spontaneous because delta G is positive. Yes.
What would be a real life example of something that has an increasing enthalpy but a decreasing entropy?
Something. Okay. What would be a real life example of something that has an increasing enthalpy
Like how are you
and
increasing,
decreasing? So we're adding heat,
but we're lowering, or
but the entropy is lowering.
how does that work?
That's a good question. I haven't thought about that before.
Because when you add heat to something, it's always going to increase the amount of kinetic energy in the molecules, which is going to increase entropy.
The chemical cold packs. So chemical cold packs, when you break them open, okay, so you got a chemical cold pack. Here's how a chemical cold pack works. So the question is, give me a real life example where heat is absorbed and entropy increases. And so the way chemical cold packs work is you have a pack of ammonium, I think it's nitrate, okay, which is also explosive if you use it under different conditions, but chemical cold packs are not those. And then you have water out here. And when you break that, you mix these, right? So entropy is increasing. You also dissolve, you spread those things out. Entropy is increasing there. Oh, you want a decreasing entropy though. Yeah. Okay, that's not going to work. But this is a case where, so you want a process where we're adding heat, right? That makes it non-spontaneous, and then we're increasing. So I don't have an example because it's not spontaneous.
So that problem is just entirely made up. Like it
Yes,
can't have a negative
yes.
entropy. Okay.
That's it wouldn't be a spontaneous process. You would have to add something. You'd have to couple it to something else,
It
and
would
we're
have
going
to
to
be
see
an
that.
energy coupled reaction.
Yes. Good question. All right. So we did that one. We're going to skip this one, and we're going to let's get on to actually talking about coupled reactions. Okay, so this is a really important process. I'm going to give you an example of a coupled reaction, but one thing I want to say is that I haven't said yet is that free energy is a state function. So remember, a state function only depends on the beginning and end states. Doesn't matter how you get there. So free energy change is equal to our enthalpy change minus our temperature times our entropy change. We said that entropy was a state function, right? Doesn't matter how you get from one, it just matters what the starting entropy was and the ending entropy. Temperature is a state function. It doesn't matter whether you raise the temperature or lower it 6 times or just go up to one temperature, it's still the same temperature. Enthalpy is a state function. All these things are state functions, so free energy is also a state function.
Is that what we talked about when we talked about glycolysis, how it's like a couple of reactions and it's just has to do with the start of an ending thing for the Gibbs free energy because it's technically negative even though you have to like put energy in.
That was complicated. Ask me while we're working the next problem. Okay, I didn't exactly follow. But so let's go ahead and just, what this means is we can add reactions together. Okay, so we can add reactions together when we do this. And so I'm going to give you, here's my example. So I can also add the free energies together as well. Okay, so I could have a reaction here where My free energy for that is 561.2 kilojoules. Okay, is that a spontaneous reaction or not? It's not. It is spontaneous, right? Because it has a negative free energy change. And then I could also take that lithium oxide and I could dissolve it in water and make solid lithium hydroxide. And that would have a free energy change that looks like this. All right. Is this reaction spontaneous? It is not spontaneous, right? Because it has a positive free energy change. But I can add these two reactions together, and if I add them together, I also add these. So I'm going to go ahead and add them together, and if I do that, notice that we have a lithium oxide on the reactant side and a lithium oxide on the product side, so they cancel. I don't think anything else cancels here. It does not. And so then I can add them together and go lithium solid plus 1/2 oxygen gas plus a water that's a liquid goes to make lithium hydroxide. And if I add those two reactions together, I need to add the free energies together. All right, so I can add those free energies together. And what I get when I do that is negative 201.9 is actually correct. Sig figs here, kilojoules. Is this reaction spontaneous? Yes. All right. So I can couple reactions where I have a reaction that's not spontaneous. I can couple it to a reaction that's spontaneous, and the overall reaction could be spontaneous. So many of you are in this class because you had to take it for some other major, like you're a biology major or you are a HEX major or something. You're interested in doing things that are medical, right? And so in biological systems, this is really useful, not this particular reaction, but it's really useful to have couple a non-spontaneous reaction to a spontaneous reaction. So an example of this, I'm not going to write all the formulas out for time here, but a really basic example that you can't go very far into any of those fields without running into is that the first step in glycolysis, so glycolysis is one of the first processes for breaking down glucose, is that you need to take a glucose and you need to combine it with a phosphorus, okay, to make glucose 6-phosphate. All right, and that I should have looked this up, I guess, but that's about 15 kilojoules per mole. Okay, that's roughly what that reaction is. So spontaneous or not?
No.
Not, but it has to happen. Okay, so I think when we do this, we also eliminate a water. So the way your body does this is it couples this reaction to the hydrolysis of ATP. So if I take ATP and I combine it with water, I can make ADP plus a phosphate. And that reaction has a free energy change of negative 30.5 kilojoules per mole. Okay, so these two reactions get coupled together. And what I can do here is I can cancel waters, common waters on both sides, common phosphates on both sides. All right, and then I get glucose plus ATP goes to glucose 6-phosphate plus ADP, right? That's what's left. And I can add those two reactions together, and now I have a spontaneous first step for glycolysis at negative 15.5 kilojoules per mole. Does that make sense? So biological organisms do this all the time because building you up is not a spontaneous process. It takes energy. The universe wants to spread all that energy out, and you by existing are concentrating a bunch of energy in you. Okay. So we're essentially By existing, what you do is you create more disorder in the universe, right? You break down molecules, you cause more disorder so that you can be ordered. Questions? All right, so now we're going to do a kind of tough problem with this. All right, what I want to do is, this is a problem, I love this problem because it has everything in it. And so we're going to go ahead, and I want you to kind of try to start it. But what I want to tell you is, we talked about this before. If I need to flip a reaction, what happens to flip the products and reactants? What happens to this? I flip the sign. Okay, we did that with our enthalpies before. And then what if I have to divide a reaction by a number? Let's say I divide one of these by 2. I would divide that by 2. Okay? Go ahead and get started on this. What have we got? 14 minutes left. I'm going to step out for the bathroom. Sorry, I teach too many classes in a row here. But go ahead and work on that while I do that, and then we'll come back and work on it. But you're going to need to use all 3 reactions to add up and make the reaction at the top. And you're going to need to flip some of them, and you're going to need to divide some of them by numbers.
I think I can actually do it as a unless I'm Wait, 7? No, 3, no, they do it. Wait. Oh, wait, you flipped the first. You have to flip both. Yeah, they do.
Don't go with tight areas. I'll be on the go.
Did you snap the first one? The second one?
Okay, some of you look bored. Already solved it? That's great. Okay, so let's take a look at this one. If you're confused on what to do here, how many people are done? Okay. All right. So let's go. Have more time. Let's start it because I need to get through this, right? We need to definitely get through this. So let's talk about hints on how to do it, though. When I look at this, I need to figure out which ones I'm going to need to flip, right? To figure out whether I'm going to need all of them. So let's look at what's in here. There's a C2H4. Do any of these have a C2H4 in them? Yeah, this one does, right? Do any of the other ones have a C2H4 in it? No, so I absolutely need this one, right? C2H4 is a product or reactant on this one. It's a reactant. So, and up there it's a product or reactant. Reactant in both cases, right? So I need to, don't flip, That one, because it's on the right side. How about this, H2? Which of these has H2 in it? This one has H2. Any of the ones have H2 in it alone? No. So I need this one too. And so H2, is H2 a product or reactant here? Product. Is it a product or reactant here? Reactant. So I'm going to need to flip this so it's a reactant. Okay? So now this one, C2H6, where is that? It's first reaction, right? So I need the first reaction because it's only in the first reaction. And there it's a product, here it's a reactant, so I need to flip. Okay? Now, we have an interesting situation in that these three things up here, we're only in each of these ones, right? They're only in one of these. So how many of these do I need? I need one of those, but there are two. So what do I have to do? I have to divide everything by 2 here. Divided by 2, divided by 2, divided by 2, divided by 2. And what do I do with the delta G? I divide by 2. Okay. How about my H2? There are 2 here. How many are here? 1. And this is the only place we had H2, so they're not going to cancel. So I'm going to need to, once again, divide by 2, divided by 2, divided by 2, divided by 2. Okay? And then how many of these are there? 1 here, 1 there, we're okay. All right, so I'm going to go ahead and rewrite all of them so I can add them together so they're all the way they're supposed to be. So I've got this bottom one that I'm not flipping. So what I'm going to do is I'm going to just go ahead and draw a line here. I don't need to do anything to this bottom one, right? So I'll just keep it and I'll write below it. So I'm going to go and flip this one. So I'm going to have, and divide everything by 2. So I'm flipping this one. So I'm going to go O2, but it's 1/2 O2 because I divided by 2, plus H2, right? So I divided by 2 goes to make H2O. And then my delta G for that is going to be half of that, which is 220 something or other. $228 is 228.6 kilojoules, right? I did flip it. Good. Good catch. Okay. So, and then I'm going to flip this one as well and divide by 2. So I need to do that now. So I'm going to start on the right-hand side. So I've got 3 waters. That's this instead of 6 waters. I have 2 carbon dioxides there. Instead of 4 carbon dioxides, I have 7 halves oxygens, okay? Instead of 7 oxygens, and I have 1 C2H6 instead of what you see here, and then my delta G there is going to be equal to the other thing divided by half, so it wasn't 290, 17.2, and I get positive, right, because we flipped it, we have to change the sign, 1458.6 kilojoules. Does that make sense what I did there for both those? And now I'm just going to add it all together. So I'm adding everything below that black line up. First off, let's go ahead and cancel some things though. So what have I got? I've got half oxygen here, right? And then I've got 3 oxygens there for 3 halves oxygen. 7 divided by 2 is 3 halves, right? So these are on the reactant side. This one right here is on the product side, so I can cancel those. All right. Carbon dioxides. I have 1 carbon dioxide on the 2 carbon dioxides on the reactant side and 2 on the product side. All right. Over here, we'll do this in gray, I've got 3 waters on the reactant side, and I have 1, 2, 3 waters on the product side, so I can cancel those. You could write this all together, all reactants, all products, and then do that as well. This is just less writing this way. And so now I think I've canceled everything I can cancel, so I need to bring things down. So I have this left, I have this left, and I have this left. And so I'll bring those down, and I have C2H4. Now I'll actually put my states back in gas, and that's good. Plus, I have hydrogen gas, goes to C2H6. All these are gases. And do you see that that matches what we've got at the very top here, right? This matches, so we add them together, they match, and now we just need to add together all of these. Our free energy changes there. And I should get 84 if I remember last lecture. Yep, 84.4, negative 84.4. So my free energy change is equal to negative 84. Questions on this? Okay, kilojoules, don't forget your units. All right, super important thing to do, we're gonna use that. We still have 4 minutes. Let me see what else we can do with that. Other questions though while we're waiting? Okay, does it all make sense? That was pretty complicated. That's about as complicated as it would get. But you do need to know you're going to divide. You divide. This gets divided to, and you do need to know if you flip an equation that we're going to change the sign on whatever our output is there. Let's go ahead and we're not going to do that. That's going to take too long. What else did I have here? Let's do this one. Give you a minute. Give you a minute to get as far as you can. I'll take a minute to get as far as I can. Okay, so what I want you to do is you've calculated for one of them, hopefully calculate for one of them and then predict all the rest as fast as you can. Okay, I'm going to calculate at the melting point. So what do we do at the melting point here? So this is, once again, we're going to use delta G is equal to delta H minus T delta S, right? And so then at my heat of fusion is going to be, I'm going to, for real quick here, I'm going to just do my conversion to joules in my head here. So that's going to be 13,260 joules per mole. Minus my temperature at the melting point is going to be, oh, they told us what it was in Kelvin. How sweet. Okay, times the entropy change, which is going to be 9.766 joules. So increase, when copper melted, the entropy increased. Did that make sense? Yeah, you go from a solid to a liquid, you expect entropy to increase. Okay, so let me go ahead and calculate this real quick. So I've got 13,260 minus 1357.7 times 9.766. What do I get? I get 0.7, something really close to 0, right? So in terms of significant figures here, actually, it is 0. Okay? You don't have to do this. Don't worry about the significant figures. Did I already say it in this class? You know, if you've got a significant figure, I'm going to call it that. Okay? I would give 1 or 2 significant figures because you can just be off by 3, right? You don't want to give 0. You don't have one significant figure when it isn't. But it would be here. So at the melting point, this is what I predicted, it would be 0, right? We're in equilibrium between the two type things. Below the melting point, spontaneous, what do you expect? If I have copper sitting here, would it melt? No. Above the melting point, spontaneous? Yes, that's what you should get from this. And it should match your expectations. All right, you guys have a great weekend. Enjoy family weekend. Go to Epics if you need them, please. Easiest 5% you'll get in the course.